Welcome back. This is Emmett, and in today's video we'll be tackling this problem. The equations y equals x squared and y equals x create an enclosed region. Find the volume of this region revolved around y equals x. So pause the video, try it out, and then get back to the video when you're ready. Okay, so I'm going to start by drawing a visual here. So we have the line y equals x, and we have the curve y equals x squared. And it creates this region here, and this is what we have to revolve around the line y equals x. And so if you've taken a calc course, you're probably familiar with integrating with respect to x, which would be getting these distances, or with respect to y, which would be getting these distances. However, we need to utilize the perpendicular distances here and then integrate by revolving these distances. In part 1 of this video, Mari showed you a straightforward way of how to solve this by rotating axes. But I'm instead going to offer an alternate way of solving this. What we're going to do is create an equation, a distance equation, that gives the perpendicular distance from the line to the curve at each x. So just to draw this out, say we plug in 0.2 to this unknown equation. What it's going to do is give the distance from 0.2 to the point along the curve y equals x squared that's also on this perpendicular line here. And so I already found at this point, prior to the video, I found that this point is 0.305.095. And so the output of this distance equation will be the distance between this point and this point. And without getting too far into it, we will have something we can then integrate. So if this is a little unclear, it will make sense soon. Let me clear some room and we'll begin. So I'm going to start by labeling these two variable points. We're going to have x1, y1 for the variable point along the line y equals x, and we'll have x2, y2 for the variable point along the curve y equals x squared. And our equation will be the distance between these 2 points. So using the distance formula, we have x2 minus x1 squared plus y2 minus y1 squared. But the problem is we can't have all of these variables. In the end, we're going to need to have an equation with just one input, which we will eventually get to be just x1. But for starters, what we can do is we can replace y1 with x1. Since the equation y equals x, y is always going to equal x. So I'm just going to write x here, x1. And so now we have to think about how to get rid of, or rather write x2 and y2 in terms of x1. And so first of all, we know that this is perpendicular, right? And this point, this variable point, is always going to fall along this perpendicular line. And so what we can do is find the corresponding perpendicular line that goes through x1, y1, and then find where this line equals the equation y equals x squared. And where these two lines, the line and the equation, equal each other, this will be x2. And then y2 can be derived from that as well. So because the slope of the line y equals x is 1, the slope of the perpendicular line will always be -1. And so to find the equation, we can use point-slope form, which is y minus y1 equals the slope, so -1, x minus x1. And again, y1 equals x1, because the line y equals x. And so isolating for y, we get y equals negative x plus 2x1. And so now we have this equation for the perpendicular line going through the variable point x1 comma y1. And what we can do is set this equation equal to the curve of y equals x squared, and this will give us x2. And so let's do this. We have negative x plus 2x1 equals x squared. And so let's move the x's to the same side. We have x squared, plus x equals 2x1. And so now we're going to do some completing the square. So we have x plus 1/2 squared equals 2x1 plus 1/4. So now if we take the square root of both sides, we get x plus 1/2 equals square root of 2x1 plus 1/4. And so then we get x equals square root of 2x1 plus 1/4 minus 1/2. And so this x, this is the x where the perpendicular line, the variable perpendicular line, since it can change, and the curve y equals x squared, where the two equal each other. And so because of this, this x is x2. So now we have x2 in terms of x1, and we can also get y2 in terms of x1, since y2 is always just going to be x2 squared. So let me write that out. So we have y2 equals square root of 2x1 plus 1/4 minus 1/2 squared. And so now we have both x2 and y2 in terms of x1. And so that means that we can replace both x2 and y2 in the distance formula to get an equation that's the distance, and it's going to be all in terms of x1, which looks something like this, as you can see here. Alright, so I've drawn out this equation down here in yellow, and you can see that it has a similar shape to the original equation. It has the same oblong shape and has the same maximum thickness, this perpendicular thickness here, right? However, it is compressed, whereas this distance here, from here to here, is square root of 2. This distance from here to here is only 1. And so we need to stretch this equation in yellow so that this shape has the exact same proportions as the original shape that we want to integrate. So if you remember stretching and compressing equations, we can divide each x1 by square root of 2, and this yields this new equation here. So now we have this equation here, right? And just to draw this out, this has the exact same shape as the original shape that we want to integrate. That's not perfectly drawn, but you get the idea. And so now we're going to integrate from 0 to square root of 2, since this new distance is square root of 2, just like the original shape, of g of x1 squared dx, and then multiplied by pi. And if you plug that into your calculator, you should see that this yields 0.07404, which is the exact same answer that Mara got in part 1 of the video. So I hope this alternate way was interesting and demonstrated that there are different ways to solve the same problems.